and record here as well. So we got double recordings. All right. We are being recorded. Audio and video is up. So everybody should see the slides. I think that, I don't know what happened, if that broke up a little bit there, but let me know if anything causes too many technical issues. So everybody, welcome back to Steel Design. We've got I've got the first homework graded. Everybody did pretty well. The one comment I would mention on the homework assignment, and when you're doing factored loads, there are a series of load combinations that you go through, but ultimately what you want is the factored load, the one that governs. So there were a number of you that went through all of them, but what you want is the answer. Like if I'm designing this beam, what do I design for? And there's 7 different load combinations, but you want the one that governs. You want the biggest. The other thing I would mention is just to make sure that you take your time on the calcs, because there were some of you that had a couple calculator issues, and this is the type of math that you'll be doing throughout the semester, and I'm hopefully that's reassuring, because again, we're not doing anything that's from a computational perspective that's very difficult in this class. So hopefully that gives you some reassurance. But just make sure that you're taking your time, dotting your I's, crossing your T's, checking your calcs, and what have you. Okay, so we're done with fundamentals, as it were. In other words, that up until now, we've really just been sort of setting the stage for steel design. And what I want to do now is to actually start talking about some steel design. Now, I want to actually show you something real quick. Let me show you something here. Yeah, go ahead.
I'm not sure. Maybe I did it wrong, but I think you may have got problems. I think question 4 and 5 switched up. This was the one related to the ASTM metals, the type of steel.
Did I have a typo?
Well, I think you got to switch around based on the grades, because I was checking the manual, what you said, and I think question, I can't remember the exact questions exactly, but on the one related to the I think was it, I got to find it here. Here we are. On A618, there was no grade 55. There's only grade 3 and grade pounds and 2.
Hold on. If I have a typo.
Really? There was? I must have missed it or something.
Yeah, it's right there. A529 grade 55 and A618 grade 3. Yeah, they're both there. We'll look at it when I grade. If I see something on your homework, I'll make sure that there are some comments there that go through. I left comments on all of the homeworks that I graded last. So I think that you should have some pretty clear guidance, and I'll make sure there's clear guidance on this homework as well. I'm just curious, is anybody else experiencing some camera feedback? Because I'm viewing the lecture on my desktop, and it's really lagging.
Same here on my end.
Huh.
Wait, now it's stabilized for a moment. Just a few seconds ago it was like.
I think it might have been the way I had my my computer set, because I think it might have been getting hot. But I'll mess around with that. If I have to go back to some other tech setup, I will. Any other questions before we get into tension members? Okay, so I want to show you what I drew here on the board. This is about the best artwork. Hold on. I want to show you the what I have here on the board. This is about the best artwork that you can get out of me. But I wanted to illustrate what we're talking about in this class. And so I know I've drawn everything as boxes and not eye shapes because I kind of ran out of patience when I was drawing the image. But what I have here is sort of a conceptual view of a framing plan of a building. And you know, it's a really simple framing plan. There's just, you know, 4 columns and a few beams and whatnot. But this framing plan really does demonstrate everything that you would find in a building like this, okay? And there are really four main elements that go into a framing plan like this. There are the beams, you know, the elements that are designed to be bent. There are the columns that are, you know, pushed down and want to act like this. There are the connections, either bolted or welded, but the connections that connect elements together. But then there's also the braces, and these are the elements that keep the building upright during, you know, lateral events. Now, this isn't the only place that you would find a tension member, but in a building system, this is one of the most common. The other being that if you were designing a truss, remember when we do truss analysis that you have members that can be either in tension or compression. Tension members are just that. They're members subjected to tension. And traditionally, whenever you start to learn steel design, you always start with tension members for 2 reasons. One, the mechanics are easy. That if you look at the big picture of steel design and structural mechanics and structural engineering, tension members are a very easy place to start. You have sigma equals P over A. If you understand that, you understand tension members. But the other reason why we tend to start with tension members is because we're trying to introduce you to this. There are going to be standards and specifications that we need to follow in order to design and detail steel members. And starting with tension members is a great way of getting you down that road to understanding that. So that's why we're starting with tension members in the class. Your first exam is going to be on the fundamentals that we talked about up until today, and then on tension members. So for the next 2 or 3 weeks, I want you to think solely about elements being yanked on. Now, that was a question from Harrison. Can a tension member be a cable? So cables are subjected to tension. There are different design expressions that we would use for cables, and we can talk about that if we have time. One thing I will say, we do talk about not just hot rolled sections and plates and whatnot, but we talk about eye bars and tension rods as well later on. If we have time, I might try and introduce some of the items related to clevises and things like that, but my end goal is just to make sure that you get that general bracing element component to the science, if you will. Let me pull up the slides. So let's go back to this. Hold on, I cut out again. I think my surface is getting hot. I think that's what's going on. That's why it's cutting out a bit. If it gets too bad, let me know. All right, so remember that we talked about the concept of a limit state. So this is that condition that we define such that if the loads exceed that condition, it no longer fulfills the design criteria that we're interested in. And we tend to deal with 2 different types of limit states: strength limit states and service limit states. In tension members, we will look at both. Our strength limit states will be related to yielding and fracture, and then there's a weird one called block shear, which we'll talk about near the end. And then we'll also consider a service limit state related to a member's slenderness. But we'll get to that as we go. But the big picture I want to convey is that with tension members, we actually get to handle both of these. So it's a nice introduction to everything going on. Now, when I said that the mechanics are easy, I meant it. So you have members subjected to axial tension. They are the most basic of structural elements. The mechanics are really simple. So you have an element. You are yanking on it with some load, like 20 kips. It's 4 square inches around. That's how big around it is. So if it's 20 kips, it's 4 square inches. 20 over 4, it's experiencing a stress of 5 KSI. That is the mechanics in a nutshell. So if we're trying to look at this from a design perspective, if we chose some limiting stress, so we said, okay, we don't want the stress to exceed Fy, for instance, the yield stress. So we take the yield stress times the area, and then that tells us the maximum load that the section can withstand. If you understand that, that's the theory in a nutshell. There are some detail related parameters that we're going to have to discuss because it's not as simple as that from a nuts and bolts standpoint, no pun intended. But the theory and the mechanics, that's about as simple as it gets. Now, one thing that we're going to talk about today, though, is the area. So, again, if we're talking about stress, stress is P over A. The area matters, okay? So what area are we talking about? Well, we're actually not talking about one section, we're talking about two. And we have names for those. We call those the gross section and the net section. There's a reason why we look at both areas, both from a behavior and from a specification standpoint. But right now, I'm just interested in the terminology aspect. So let's say I have a tension member, and I'm taking that tension member and I'm yanking on it. So I have here on the slide a very simple schematic of what a tension member would look like. And I'm trying to introduce some real life aspects that you need to consider because, in real life, you're going to have, this tension member and it's going to have holes drilled in it on the ends. There's going to be, some component where, you're going to have to affix this or connect it to another member. So now we could use bolts, we could use welds, but the point being is that there is a difference between what the member looks like in the main body of the member versus what it looks like near the connection, okay? And so we have two names for those. We call that the gross section and the net section. The gross section being if I samurai sworded or lightsabered through the main body of the member, what is the section that I'm looking at? That's the gross section. The net section is what it would be like if I samurai sworded or lightsabered through the section right there at the connection. If I'm yanking on this, it's going to fail really in one of two locations. It's going to fail, right here in the main body of the member, or it's going to fail, right here along this edge of the connection. And so those two different sections are going to have two different areas, and those two different areas are going to be subjected to two different limiting stresses. So we're going to have two different limit states that we're going to have to assess. Now, for the net section, and this is, I actually typically don't put this in my slides. This is some sort of new material, but because we're doing this virtually, I want to make sure that everybody's on the same page. So number one, tension members are usually symmetric, right? They tend to look the same over here as they do over here, okay? So what that means is we can tend to only look at just one side, and more often than not, unless the connections were different, that's very rare in a lot of these instances. There are some instances where that can change, but more often than not, it doesn't. But we usually don't need to look at both sides. We can usually just look at one. The other thing that's important is that we are considering the section that passes through what's called the lead line of bolts. To be honest, for today, that doesn't really matter, but that will later, okay? So later, assessing the lead line will be important. For today, it won't affect anything. Any questions? All right. Okay. Now, I want everybody to open their manual, okay? I want everybody to grab their manual, and we're going to the specification, okay? So remember, that's the section in the back with that's in front of the gray line pages, and I want everybody to turn to Chapter D, okay? So we are going to open the spec, and we are going to start to look at this today. All right, so it's going to be on 16.1-28, and you should see something that starts to look like this on the page. And if anybody in the chat is having an issue finding that, I want you to let me know. So if you can see here on the camera, I am sort of in, sort of like in that part of the manual there. And on the top of the page, you should see design of members for tension. That's what you're looking for. All right, so I'm going to give everybody a sec on that and see if anybody has any questions. Finding it, that is. One of the things I'll mention throughout the class is there'll be plenty of times where I say, turn to this page or turn to that page. And I'll give you some time to do it. And if anybody's having a hard time finding it, let me know in the chat. Otherwise, I'm going to assume that you found it. Okay, so again, if you need help finding it, let me know. But otherwise, I'll just blanketly assume that you're able to find it. Now, if you look at Chapter D, obviously that's the chapter that we're looking at, or that matters to us right now because we're saying design of members for tension. The very top of the page says, okay, the chapter is organized as follows. There's slenderness limits, tensile strength, effective net area, so on and so forth. Okay, I want to focus on section D2, which is the section on tensile strength. We'll actually go back and talk about section D1 and particularly this user's note in D1 later on. But for today, I want to focus on D2 and D3, D2 and D3. Okay, so D2 says that the design tensile strength of tension members shall be the lower value obtained to the following, according to the following limit states. And so we have listed tensile yielding in the gross section and then tensile rupture in the net section. And so what that means is whenever we look at a tension member, if we're looking at the gross section, we limit the stress to Fy. And for the net section, we limit the stress to Fu. Okay. Now, behaviorally, why do we do that? Well, if we're talking about the tension member, okay, remember the behavior of steel and how steel behaves when you apply load to it. So if I take this member and I yank on it, it will behave elastically until I hit the yield stress. And once I hit the yield stress, I will start to experience permanent deformation. So remember, once you exceed Fy, if you let it go, it'll be permanently elongated. We do not want the gross section of the member to permanently elongate, because what that means is if I have a structure like here on the board, like imagine I've got this framing plan and suddenly this brace is longer than it is supposed to be, like it's permanently elongated. Well, that's going to cause unintended stresses on the other members. So we don't want the yields or the gross section to exceed the yield stress. But the net section occurs over such a small area of the member. Like here's the tension member. The net section is just this little bit right here. And as you're going to see here later on, the stresses around the net section are a little weird anyways. There's a lot of stress discontinuities, and it's not as simple as the pretty P over A picture that we'd like to use. So we say, okay, we're going to limit that stress to Fu, to the ultimate tensile stress. But a couple of things are gonna be impacted. Number one, we're not going to use the net area. We're going to use this term AE, which is the effective net area. So we're going to take the net area and we're going to reduce it a bit because of those weird stress discontinuities. That's one thing to keep in mind. Another thing to keep in mind are the resistance factors. Okay, so these are those phi values. Okay, so if you look here on the slide, you should see this, or on the page, you should see these phi values here and here. Now, whenever you look at the phi value for rupture, it tends to be lower than the phi value for yielding, because those are resistance factors that are intended to ensure uniform safety. Okay, so if a member yields and it gets longer, I mean, that sucks. We don't want the member to experience permanent elongation, but that's not as bad as if it fractures. I mean, if it fractures, the member is separating. That's bad. So we use a lower resistance factor because we're sort of making sure that the usable strength is lower to account for that, worst case scenario, if you will. So we're going to get to computing the capacities and the limit states later. Today, what we're going to focus on are the gross area and the net area, because what you'll find with tension members is that there's really two challenges. If you can compute the areas and compute the shear lag factors, which is what we'll talk about a little later, then tension members are not bad at all. So we take it one step at a time. So let's talk about the gross area and let's talk about the net area. So in general, for bolted connections, this would be the basic formula, the basic idea. That for bolted connections, the net area equals the gross area minus any area that you have removed from the connection due to the presence of bolt holes. Okay? Now we're going to develop a more specific formula soon for AN. So don't worry, I'm going to take this, sort of conceptual formula and refine it a bit later. But for now, in order to develop the net area equation, we're going to need three quantities. Okay, number one, we're going to need the gross area. Like in order to compute the net area, you need the gross area because the net area is the gross area with material removed. You're going to need the thickness of whatever plate or element the bolts are passing through. You got to have the thickness. And you also need the diameter. And notice how in this slide I'm not really defining what I mean by the diameter. Okay, so let me talk about that. In the world of steel design, there's actually sort of three diameters, specifically in the world of tension members and connections, there's three diameters that we need to consider, okay? So first off, I want to talk about the diameter of the bolt and the diameter of the hole, okay? So if anybody has ever done any type of work in a garage or done any type of work with their hands where they're bolting stuff together, anything, worked on a lawnmower, worked on their car, anything, you would know that if you have a 1/2 inch diameter bolt and a 1/2 inch diameter hole, that's not going to work. You're not going to be able to fit those together. You actually have to physically drill the hole a little bit larger so that the bolt can go through the hole, okay? Whenever you look at mechanical connections, the holes are just a little bit larger than the bolts, okay? And so we call that erection tolerance. For standard size holes in steel design, in structural steel design, the holes are drilled 1/16 of an inch larger than the diameter of the bolt. So that's why I have, I've got the diameter of the bolt here, but then the diameter of the hole, the hole is a 1/16 of an inch bigger. Okay, and for standard size holes, that is the standard increment of increase. Now, so there is a difference between the diameter of the bolt and the diameter of the hole. Now, in tension member land, when we are accounting for the diameter, we add another 1/16 of an inch on top of that to compute what's called an effective hole diameter. The idea is that whenever you have a tension member, you drill the hole, but if any of you have ever seen steel holes drilled, there's burrs, there's just this little ring of material that we don't really consider effective in transferring stress to the member as a whole. So we add another 1/8 of an inch on top of that, another 1/16 of an inch on top of that, just to account for that ring of damaged materials. And in the slides, I'm referencing where that's coming from in the specification. So if you want to know the diameter of a hole for a tension member, you take the diameter of the bolt and you add 1/8 of an inch. And the reason you're adding 1/8 of an inch is because you're adding a 1/16 twice. 1/16 of an inch accounts for the erection tolerance. 1/16 of an inch accounts for the fact that little lip of damaged material around the hole we don't consider effective in transferring stress to the member. Now, before I open it up to questions, I am going to say one thing. You all are not going to like me later on in the semester when we look at bolted connections, because when we are assessing the limit states related to bolted connections, we don't use the effective hole diameter, we use the actual hole diameter. So when we get to bolted connections, we're going to add a 1/16 of an inch. For now, you're just going to add 1/8, but later on, you're going to add a 1/16, and you're going to go, dang it, Dr. Mike, why can't you just keep it consistent? So my apologies for that, but that's steel design. Okay, before we get into our example today, I want to see if there's any questions. Okay. Let's do some math. Okay, so today we're going to do two examples looking at gross and net area, and I want to compute the net area for the plate shown, okay? So this plate is 8 inches wide and it's 3/8 of an inch thick. So that's what, when I say 8 by 3/8, I mean, it's 8 inches this way, and in and out of the screen, it's 3/8 of an inch thick. I've got 2 lines of bolts, and so there are 4 bolts per line. And the bolts that we are using for this problem are 3/4 inches in diameter. And I'll go ahead and tell you, in the world of steel design, 3/4 inch diameter bolts are among the most common. Really, you'll find in real applications that 3/4 inches, 7/8 of an inch, and 1 inch diameter bolts are what we're using for just about every project. If you were using larger bolts than that, that would probably be pretty specialty, I would think, a very unique system. And also, just so you're aware, if you ever see me draw a break line, it just means that the main body of the member, like the gross section, goes out that way. So the member continues on, you know, in that direction. Okay, so let me end the show. Let me pull up my notes here. Okay. All right. So everybody should see the example here. So this is the example that we're talking about. We have the net area for the plate shown, and let's see if we can compute the net area. So in order to compute the net area, the first thing that we're going to need to compute is the gross area. Oh, you go away. All right, so help me out. Can somebody tell me how we would compute the gross area of this plate? And I promise I'm not trying to give you a trick question here.
Don't we need to know how long this plate is?
That's a great question. And let me say two things. We will need to know how long it is later. But remember, we're talking about areas of cross sections. So we're talking about the samurai sword lightsaber perspective.
Got it.
So now, Mr. Ball mentioned the area of the plate minus the area of the bolt holes. That's for the net area. Okay. So right now, remember the formula that that he mentioned was AN. Hold on, give me a sec. I think it's this one. Yeah. Give me one sec. So the formula that Mr. Ball mentioned was AG minus the area lost due to bolts. And that's the net area formula. But in order to compute the net area, you got to get the gross area first. So the gross area, and everybody, I've seen this in chat, it's right. So we know that the plate is 8 by 3/8 of an inch. So it's just 8 inches times 3/8 of an inch. And so that is 3 square inches. I don't know why the screen is flashing like that. I might have to see if I can change some settings on my computer to do that. If that ends up being a problem, we'll do our share another way. In fact, let me see what I can do there.
Dr. Michelson, are we doing both sides of the plate or only one side?
Well, we're going to assume that this is symmetric, so either side it's not going to matter. Do you see what I mean? But I get the feeling I might not have addressed your question, so help me out with that.
Okay, can you again explain where 3/8 of an inch fits into like the dimensions of the figure that we're seeing?
I'm saying that no. All right, I'm saying that the plate all right, so here's the plate, here's the bolt holes. Man, I'm having some lag today. I don't know what's going on.
Yeah, you were frozen for like probably 10 or 11 seconds there. I couldn't hear what you were saying.
I don't know what's going on with the lag today. I'm going to try something. Give me 1 second.
The plate is 3/8 inches thick. That's how we got.
Yeah. So this dimension here is 3/8 of an inch, and this dimension is 8 inches. Let me try something. Give me 1 second. Let's see if I can address this lag a bit. Let's see. Does that address the hopefully that addresses the lag a little bit. Let's try that. Okay. So what I'm saying about the 8 3/8 is that plate is 8 inches wide and it's 3/8 of an inch thick. So we're talking about the cross-sectional area of the plate. Does that make sense?
Okay, that's the key right there. Cross-sectional. I thought you were talking about the face that we were seeing. I didn't know we were talking about the cross-sectional area.
That's a great question. And to be clear, we are always going to be talking about cross-sectional areas when we're talking about this type of concept. Give me 1 sec. I'm going to turn my touch screen off because it keeps popping up. I thought I had turned that off, so bear with me. I'm going to turn the settings on my touch screen off so that I don't keep pulling up the keyboard and crap like that. I think that's one of the reasons why I keep getting the flashing. I thought I had turned that off, but see, I can still use the pen without the touchscreen. There we go. I think that'll be a little better. Okay. So is everybody clear? I know we've hopped around a bit on the technology, but is everybody clear about the area? And we're talking about that area there, the area of the gross section. Just if I cut a samurai sword through the main body of the member, that's what we're talking about. Okay? All right. Now, help me out on something else. Okay? What is the bolt diameter? Okay? So, or sorry, not the bolt diameter, but the hole diameter. So, well, now, okay, so the bolt diameter is 3/4 of an inch. So just want to make sure everybody was paying attention. In order to get the effective hole diameter, we take the bolt diameter and we add 1/8 of an inch. Remember, we add 1/16 of an inch to account for the fact that the hole is physically larger than the diameter of the bolt. But then we add another 1/16 of an inch to account for that damaged material. So the hole diameter is 7/8 of an inch. Is everybody else okay with that? All right. Now I want some interaction from the chat on this one. Okay. The formula states that the net area is the gross area minus the area lost due to the presence of bolt holes. So I want to poll the chat. How many bolt holes should we subtract? There we go. That's right. 2. Because we're talking about a cross-sectional view. Since we're doing cross-sectional. Exactly right. Now, this is what I'm after. Therefore, the net area is the gross area minus 2 times what? Now I want to get some interaction from the chat. We're subtracting 2 bolt holes, but 2 what? All right. So we got some controversy here. I see a pi r squared because we're talking about the area of the circle. That sounds like a good answer, but it's not the right one. The correct one is what Trevor and Gordon said, which is 3/8 times 7/8. And here's why. When you're talking about cross sections, okay? So here's the plate, right? When you look at the bolt holes and you're cutting through that section, that's what you see. You see that, as Mr. Enoch said. What we're doing is we're subtracting that. When you go through that section, you're seeing the diameter of the hole times the thickness. That's what you're seeing, okay? So it is 3 square inches minus 2 times 7/8 times 3/8. So what is the net area of this plate? .34 square inches. Do I have a second on that? There we go. Technology issues aside, we've gotten through our first problem. Okay, so are there any questions on this concept? The idea that, okay, we've got a plate, we can determine the gross area by looking at the cross section, and then the net area is the gross area minus the area lost due to the presence of bolt holes, and then the area of the bolt holes is the diameter times the thickness, and then we determine the number of bolt holes by the cross section cut. Is everybody okay with that? Any questions? Okay, now let's take it a step further. Now let's do this one. Okay, so now we're going to compute the net area for a W10 by 49. Okay, now in order to find the net area for a W10 by 49, we need the gross area for a W10 by 49. What is the gross area of a W10 by 49? How are you going to find that out?
I imagine it involves looking in that nice blue book you paid all that money for.
There you go. You look it up in your AISC Steel Construction Manual, 15th edition. Okay, so I have that Trevor listed that the gross area is 14.4 square inches. Has anybody else been able to find that? All right. Is there anybody on the call that is not able to find that? And don't hesitate if you are. That's what we're here to do. Hopefully that homework assignment that you just completed, though, got you a little bit more familiar with looking some values up in the manual. And you stole my statement there, Mr. Romans, because I was just getting ready to do that. Whenever you look values up in the manual, in the spec, whenever you reference things, it is usually good practice to reference where you're getting that value. And I'll try and be consistent with that throughout the semester, that if I pull a value or some reference from the spec, that I'll try and, indicate where that's coming from. Okay. All right. So we've got our gross area. We've got, first off, we know the hole diameter. So we know that the bolt diameter is 3/4 of an inch. Therefore, the effective hole diameter is 7/8 of an inch. Maybe I should have put that on there. Maybe I should have, moved that over and said, effective hole diameter. This is the first year I've actually used that term, effective hole diameter. I used to just say hole diameter, but I actually think this is clearer, especially now that we're doing the class online. I think it's so important that we, ensure that we're referencing things clearly. So we know the effective hole diameter. Now let's talk about the net area. Okay. Looking at this schematic, I want somebody to help me out. How many bolt holes do you think we're going to subtract? 4. Okay, that's exactly right. Now, am I missing something? I feel like there's a data point that I need that I don't have. The thickness, you're exactly right. But what are we looking up? What thickness? But, okay, 0.56, but that's the thickness of what? We need the flange thickness, exactly right. We need this dimension here. I'm going to do a little better at that. Which is T sub F. See, whenever you pull up the, a given dimension, like we can look at the schematic and we know we need that dimension. Remember, on the top left of the table 1-1, there's that schematic. And if you look at that schematic, that's T sub F. So I need T sub F for a W10 by 49, and that is 0.56. It is not 9/16. We use the decimal value. We need T sub F is 0.560 inches. And we also got that from table 1-1, page 1-28. So, therefore, the net area is the gross area minus... Well, hold on for a sec. I'm going to get to Mr. Roman's question here in a second, and you'll see where I'm going to go with that here in a second. So 4 times the diameter times the thickness. Okay, and the reason we're doing that is, again, imagine samurai sorting or lightsabering through the section. What you're going to see is this, and you're going to see 4 rectangles like this. That's what you're going to see. 4 bolts through the flange. Nothing through the web because there's no bolts through the web. If there were bolts through the web, we'd see, like holes like that, and we don't see that. So this is going to be 14.4 square inches minus 4 times 7/8 times 0.56. And then Trevor's saying that is 12.44 square inches. Am I getting a second on that answer? I want to make sure the value's right.
Seems right.
Okay. All right, any questions? Because I want to pull up what you're going to do on the homework assignment, and then I want to just sort of introduce a wrinkle into the mix. Okay, so let me pull up the homework, and there's a question on the homework assignment that'll tend to Mr. Roman's question. So, but let me do this. Oh, wrong one. All right. So here are the 2 questions on the homework assignment. I've got 2 net areas. One of them is the net area of a WT 10.5 by 31, and the other is a W8 by 18. Now, for the W 10.5 by 31, and really for both questions, you want to make sure that you're using the right values. That, if you look up a dimension, like don't just, and I'm being, I want to be very clear on this. Don't just use a flange thickness because that's what we used in class. Look at the problem, look at what's going on, and then use the values that are necessary in order to answer the question. So I want you to determine the net area of this shape. And then I also want you to determine the net area of this shape. And what I'll say about this one is really sort of probably a bit more aligned with what Benjamin was saying with his question. So, in the problem we just did, there were only bolts through the flange. That's not the case with this one. So you kind of have to think about, okay, what am I going to do? What values am I going to use, etc. I don't think this is a terribly challenging assignment, but, I'm just trying to make sure that I'm being holistic in my coverage. Any questions? I want to introduce the wrinkle that we're going to deal with on Friday, and then I'm going to call it.
Dr. Michelson, can you just say real quick what the 8 and the 18 mean in W8 by 18?
Sure. So,
I was getting confused with those.
Okay. To be clear, it will also mean the same thing up here too. But the 8, the first number is about how deep it is. It's not, if you look up the depth of a W8 by 18 or any W8, it won't exactly be 8, but they'll be close to 8. It might be 8.03 or 7.97 or something like that. So the 8 is about how deep it is. And the 18 is how heavy it is. So it would be 18 pounds per foot. So if I had a segment that was 5 foot long and I picked it up, it would weigh 90 pounds. So I might have to get my weightlifting belt on for that one.
Thanks.
No worries, no worries. Any other questions? All right. I do want to show you one wrinkle that we're going to deal with on Friday. So this is a problem we're going to have to deal with on Friday, and that's this. Okay, so let me zoom in a bit. How do we deal with this problem right here? So today, we only dealt with sections that looked like the one on the top, where the bolts were in a grid-like sort of rectangular or parallel pattern. What about when they're staggered, like what you see down below? Now, do we do this in real life? Yeah, we do this in real life, and there is a clear reason why we would do this. Why do you think we would do what's on the bottom? I just want to see if everybody's paying attention. Why would we make it? Why would we arrange our bolts like that?
It does increase the amount of material between the bolts, strengthening the material.
That's correct. That is the answer. By arranging the bolts in this fashion, we increase the area. It's now Mr. Rick said it's less holes cut out. That doesn't necessarily translate. I mean, admittedly, my schematic is probably not drawn to the accuracy it should be. And what I mean by that is this: when we design bolted connections. We'll look at the strength of a single bolt. Let's say a single bolt can hold 12 kips, and the connection has 200 kips on it. So we take 200 divided by 12, and that tells us the number of bolts. And so however we arrange those bolts, usually whether we arrange them in a grid-like pattern or in a staggered pattern won't change the number of bolts. But by arranging it in this fashion, we can increase the area along the cross section. So what Mr. Roman said, I guess that's kind of true. And everything we're talking about there might be a bit more relevant when we actually start talking about the bolts themselves, which will be a little later in the semester. In the end, now what Mr. Enoch said, whether or not I have the bolts arranged like I do up top or like I do on the bottom, they're still transmitting the same amount of load to the tension member. What makes this problem complicated is the number of sections that we have to deal with, because it's not just the net area of a section. There's actually multiple different possible net areas, and then we have to take the one that controls. And so on Friday we'll talk about how to identify the multiple paths, how to account for the fact that some of the paths are going to be diagonal, and the short answer is we add what's called a stagger factor every time we have a diagonal path. But then the third thing is, how do we figure out which one governs? That's going to be that's Friday. That's all we talk about Friday, is that parameter there. And then going back to the lecture today, if you remember from the spec, we computed the net area. Next week, we're going to try and tackle that little pesky U that you see right here. The effective net area is the net area times this U value. We're going to try and talk about what the heck that U value is even there for and how you compute those. And so if you could compute all that, you pretty much have the big picture figured out. So I just wanted to try and give you a little bit of a taste as to what's going on in the next few lectures. But unless anybody has any questions, we're not going to have to deal with Stagger or U or anything on this homework assignment. If you can do what we did today, you can do the homework assignment. Any questions before we call it? If staggering is better, why isn't it the standard? That's an interesting question. The long story short is staggering can tend to increase the length of the connection, and increasing the length of the connection means you have to increase the amount of plate used to connect the member. So for that one, it's a trade-off, because yeah, you might result in a smaller tension member, but it might result in a bigger connecting element. So it just depends on the scenario. Like what Mr. Riggs said, if you used the same amount of bolts for a parallel versus the staggered connection is going to be longer. That's a really good question. Any others? All right, well, I'm going to go ahead and stop the recording and call it. I hope everybody has a wonderful day, and we'll see you on Friday.
Hey, Dr. Michelson, I have a question about tomorrow. Can you stay on here for a minute?
Yeah, let me stop this recording here.